Hello everyone. Welcome to the Stepper Motor Driver new product update for Texas Instruments. Before we start, we wanted to thank everyone for joining this session. A quick round of introduction. I'm Renita Bera. I'm the product marketing engineer for Brushed and Stepper Motor Driver in Texas Instruments, based off in Dallas, US. Joining me today is Dipankar Mitra, system engineer for Brushed and Stepper Motor Driver, based in Bangalore, India. Like Emily mentioned, after this meeting, you would be able to download this presentation. Also, feel free to email us directly for any questions at the email mentioned here. Moving to the agenda, we would be starting with the types of application needing mid-voltage steppers today. By mid-voltage, I mean up to 50 volts, followed by typical system requirements, the must-haves, and the good-to-haves. Though we have brushed and stepper motor drivers in TI, today we would be focusing mostly on stepper motor drivers, and we would share some of the common stepper problems, and also compare us, Texas Instruments, to the other main two vendors in the market in solving those common problems. These would be followed by introduction and a deep dive session of the DRV84XX, which is the newest stepper family from TI, after which we will be opening the floor for questions and open discussion. So stepper motor drivers finds a home in all different kinds of end equipment. Some common examples that might resonate with you are appliances, printers, 3D printers, medical, factory automation, test and measurements, just to name a few. So just for a reference, here you have a block diagram for a 3D printer, which consists of multiple arms and axes that needs multiple stepper motors of varying torques and currents. Similarly, stepper motors are used profusely in medical, like in vitro diagnostics, which itself can be of different kinds, or maybe stage lighting, or sewing machines, textile machines, etc. Some of the key must-have features and the good-to-have features are listed on the right. Like, for example, low noise, great position accuracy, great thermals, smallest possible solution in terms of footprint, and also the BOM itself, reducing the BOM size, the cost, the routing efforts, are some of the must-haves. One of the good-to-have features are also stall detection. Now, before we proceed any further, wanted to take this opportunity to conduct a quick poll about the type of motor drivers you have, the voltage and current, just to make sure that we are keeping the seminar relevant to you. I will be showing the questions right now. So the questions, you would have around 2 minutes to answer those questions kindly. One minute to go. All right. 20 seconds. I see everyone wrapping up those answers. Thank you. right. 8 more seconds. Perfect. Stop sharing my screen again. All right. Thank you all for your responses. Really appreciate it. Um, so before we dig deep into some of the key devices that actually target those features that we mentioned, let's look at steppers holistically and reflect on what are the key common problems or common issues that a designer can encounter. There's a simple chart that shows which factors are system driven or system settings like voltage and which are driver settings like step rate or decay mode. Motor parameters, voltage, step rate, and microstepping are the various parameters. As you can see, speed, back EMF, BEMF, right? And current chopping may lead to tuning issues, which might lead to noise, high motor temperature, and bumpy motion. We realize, number one, noise reduction, number two, temperature control, three, smooth motion, and four, positional accuracy are must-have for most systems. Here, today, we would be using Texas Instruments' new stepper family, the DRV84XX, to compare against the top two vendors in the market to address these mentioned issues and show you the results and the technical details of this device in the deep dive section. In a nutshell, if you look at this slide, DRV84XX is an expansive family of steppers that comprises of 12 different variants, all pin-to-pin with each other, and scalable across voltage and current. On the x-axis, as you see, it's the voltage, and on the y, you have the current. So be it a 35-volt max or a 50-volt max, from 1.5 amp full-scale current to a 2.5 amp full scale, you can scale it to different power levels easily. For the next few slides, we would be using the DRV8424, the DRV8426, the DRV8434, A and the S for comparisons with the other competitions. But these are all pin-to-pin, and any performance showed on these devices will be the same for the other sister devices as well. So 84XX, like I mentioned, is a family that has integrated current sensing. Traditional stepper motors, motor drivers need two bulky sense resistors for each of the H bridges, taking up space and adding cost and routing efforts. These devices use current mirroring. Our devices have integrated current sensing, which uses which basically sense the output current and hence integrate the current sensing capabilities, saving significant BOM cost, space, and routing efforts. We achieve 4 to 5% of current accuracy with the sensing. So as you can see, for this is an older device where you're having to use these bulky sense resistors, external sense resistors. For the new generation, this is an integrated current sensing. So you do not have to use those external bulk resistors, and it uses current mirroring. It does not only integrate the resistor, but it uses current mirroring. Secondly, is Smart Tune. Like we mentioned earlier, there's an intelligent tuning algorithm that makes tuning agnostic to any voltage changes, system changes, or even back EMF, resulting in smooth, noiseless motion. Thirdly, high microstepping. This device family has 1/256 microstepping that helps with precise control and smooth motion. I will be talking and elaborating Smart Tune a little bit more in the next few slides. But before we go there, similar to what we explained earlier, this is an expansive family that runs from 330 milliohm to 1500 milliohm and is all pin-to-pin. So coming back to the issues at hand. So the first one that we had mentioned before was audible noise. We compared our device against Comp T and Comp A. Comp A has mixed decay and no stall detection, while Comp T comes in stall and non-stall versions. and has low noise decaying method. DRV84XX has Smart Tune ripple control that helps with minimizing the ripple in the system. On the same board, when Comp A and the DRV84XX was evaluated, DRV84XX was much quieter than the Comp A as shown on the graph. Similarly, on the left, it shows how we perform similarly or modestly better than the Comp T. We also have the audio files embedded in this slide so that you can hear them when I share it with you. Also, we have an app note that explains in detail as to how we achieve the better audibility. So just going into a little bit more details, noise can be magnetic, mechanical, or electrical. Some of the common ways to reduce noise is to reduce ripple, or using slow decay for tuning, or using the PWM frequency less than 20 kilohertz. DRV84XX has something called Smart Tuning Ripple Control that enables very tight ripple regulation in slow decay at high microstepping, resulting in super quiet step movements. As shown in the graph below, we compared with mixed decay, and this algorithm was at least 10 dB quieter. Secondly, tuning. Traditionally, stepper motor needs to be tuned to recirculate the winding current, and they can add a lot of effort choosing to choose the right kind of decay modes, cycle by cycle that can also impact the back EMF and hence the thermal of the entire system. DRV84XX is going to introduce, has introduced, I should say, smart tuning that has dynamic decay mode and the ripple control model. The dynamic decay mode is an intelligent algorithm that adapts cycle by cycle to provide the best possible decay solution. This drastically helps with easy design cycles, smooth motion, lesser work in choosing manually what kind of tuning you have to choose. For example, we tried slow decay and smart tuning on the same board. At a low voltage, they perform similarly, as shown. But when the voltage was suddenly increased, the slow decay board suffered loss of regulation, especially at the zero crossing, like as shown, while smart tuning was able to handle it pretty well. Similarly, with changes in frequency, at low frequency on the same board, we tried mixed decay and smart tuning, and they performed similarly. But when the frequency suddenly increased, mixed decay wasn't able to handle it, and smart tune maintained perfect current regulation. Lastly, this slide shows that when we took thermal imaging of the motor at slow decay and smart tuning at the same microstepping, the system with smart tuning ran 10 degrees. If you look at it, 70.4 to 60.6, ran 11 degrees cooler. We also have an application note that talks about the same, and I can share it with you offline as well. Third issue at hand. It has been established that systems need good positional accuracy as the smoothness quality depends on the motion accuracy of the steppers controlling the stepper motor drivers, right? We compared the performance of the 84XX to Comp A, and this time we took one of our previous generation devices, TI's previous generation devices, DRV8825, also at 1/16 microsteps at both unloaded and loaded conditions. DRV8424, which is part of the DRV84XX, excels at both, with 84XX having much better positional accuracy than Comp A, and also with respect to our TI's previous generation device, like the 8825. Thermal performance. This is very important, I know, for many customers. As mentioned, a system that needs to operate for a long time needs very good thermals. As seen here, we are comparing the DRV84XX and taking one of the variants, 8424, namely, and comparing it with Comp A, which does not have stall, and Comp T with and without the stall versions, and also with our previous generation device, 8825. DRV8424 has the lowest RDS(on) among these similar devices, similar current capability devices, and also the conduction losses are also the lowest. So if you just compare the numbers, DRV8424 is 50% lower in power loss than COMP-A and 40% lower than COMP-T. Also, as you would know, many module makers have these breakout boards that shows how big the heat sinks are with these competition and the previous generation DRV8025. This new family doesn't need any heat sinks. So you would be saving on cost, about the effort, and also pure space as well. Fifth, BOM. This is a bonus, I guess. BOM comparison. Everybody appreciates smaller systems or more integration and lower BOM cost in general. DRV84XF integrates the current sensing functionality, like I mentioned before, and eliminates the need of those two bulky external sense resistors, power sense resistors. By doing so, we reduce the BOM cost, BOM size. We also reduce the power loss and save routing efforts. Additionally, if you look at even the footprint of the DRV8424 is the smallest in size. On the right, we compare the evaluation board for each of these comps, COMP-A, COMP-T, and also a previous generation 8825. And as you can see, 8424, which is the newest device, is the smallest out there. COMP-A uses these bulky shunt resistors, and all the shunt resistors are outlined in the yellow boxes. We are 75% smaller than COMP-A, 60% smaller than our previous generation 8825, and at least 50% or more smaller than COMP-T. Sixth, comparison of current regulation. Graph 1 is COMP-A with slow mixed decay. Graph 2 is 8825, previous generation as well, with a similar slow mixed decay, and COMP-T right here with no stall version, with their own version of tuning method. Lastly, you have the 8424 and the 8434, which is basically, again, pin-to-pin, similar device, just a different RDS(on) shown below with Smart Tune ripple control. The graph below shows clearly how tight and pristine the current regulation is for 8424 and is the closest to an idle sinusoidal. Now that we're done with the must-have features in stepper motor drivers, right? Let's talk about the nice-to-have features. One of the examples is stall detection. Now, typically we have heard systems using optical encoders or Hall sensors for detection of stall conditions. Per our knowledge, majority of customers currently do not need stall detection, and only a small percentage, about 10 to 20%, need it. This flowchart shows that if a customer needs stall, the section on the right, for whether you have analog interface or PI, which basically helps you with debugging, if you need a 1.5 amp full scale or a 2.5 amp full scale, we have solutions available right now. If you need high current, as seen, here you have two choices, the DRV8434S, and the S stands for SPI, and COMP-T, which has a stall version. COMP-T is known to have a slower response time and also EMI issues, contrary to the 8434. Also, additionally, 8434S is smaller in size than COMP-T and doesn't need any heat sinks. On the flip side, if you do not need stall, we have also outlined how we compare against COMP-A, which does not have stall detection capabilities, and the non-stall option of COMP-T. And we are still smaller. We do not need any heat sinks, and we also come in the QFN package as well. All right, so now Dipankar would be going into a little bit of deep dive as to how the stall operates, or what is the stall detection algorithm that we have on our device. Dipankar?
Yeah, thanks, Anita. So, as you might know, the stepper motors always have a distinct relation between the coil current and the back EMF. So when the motor is not loaded, there is a 90-degree phase shift between the back EMF and the coil current. And then as the load starts increasing and goes towards stall, the back EMF and current are exactly in phase. So in our stall detection algorithm, we actually look at this amount of phase shift, and from that phase shift, we derive the amount of load that is there. And when that phase shift goes to 0, we detect that the motor is stalled or is about to stall. Next slide. Thanks. So there are a lot of stall detection algorithms out there from different vendors. What we have seen is most of those algorithms have certain shortcomings, like their stall detection algorithms output will have a huge dependence on the supply voltage, on the coil resistance of the motor, on temperature. So basically, those algorithms do not work well over wide change in operating conditions. But what we have done different with our stall detection algorithm is we use a decay mode called Smart Tune Ripple Control. And with that decay mode, what happens is that the ripple current is actually constant. And because of that, if we derive the math, turns out that the output of the stall detection algorithm becomes independent of the supply voltage and temperature and all the other parameters, and it only represents the change in back EMF. So that way, our stall detection algorithm is much more robust over changes in operating conditions. Next. And the other thing I would like to mention here is with this 8486 family of devices, we also help in making the PCB layout much easier because like you can see in the HT sub package pinout, all the high voltage pins are on the left side and then all the low voltage pins are on the right side. Whereas if you look at some of the computer devices, they will have the high voltage and low voltage pins all interspersed among each other, and that makes the layout very difficult. Whereas here, the layout is very easy. All the output pins and supply pins are on the left side. All of your signal pins are on the right side, so you can create a nice signal ground, and even two-layer boards are possible. And now with the QFN pin, with the QFN package, we have made sure that the pitch is 0.5 mm. So the QFN package also can be used in all sorts of industrial applications. And both of these packages have exposed pads. Of course, the HT sub being a larger package, has a little bit better thermal compared to the QFN package, but it gives you the flexibility of either optimizing your thermal performance or optimizing your solution size by going with the QFN.
Perfect.
Back to you, Ranka.
Thank you, Dipankar. Thank you. So, all right. So now that you have seen the benefits and results of this family compared to competition and also our own previous generation devices, let's come back to the family again. Again, on the x-axis, we have the current, and on the y-axis, we have the supply voltage. Everything in red dotted line is pin-to-pin. So all of these devices are pin-to-pin. So be it 35 volt max or a 50 volt max, 1.5 amp full scale to 2.5 amp full scale, these are all pin-to-pin. Along with that, these devices provide flexibility in terms of interface too. We have step DIR version with an indexer in the device, and we have the phase enable version, which allows the customer to use an external microcontroller, or you have the PWM interface version that enables you to drive two brushed motor drivers with one stepper motor driver, because stepper motors are like 2 H bridges, and for one brush, you need 1 H bridge. Along with that, on the top right, you have the 8434, 8434A, and 8434S, 3 versions. Out of these 3 versions, the DRV 8434A and the S has the stall detection capabilities that we mentioned a few minutes ago. A stands for analog stall. So basically, you would need GPIO's hardware interface, and the S stands for SPI version stall. Well, it doesn't end there. We also have a non-pin-to-pin, but the smallest stepper motor driver out in the market, the DRV 8428, as shown on the extreme left. It's a 1 amp full scale device, and we realized that at this power level, customers care about size. So this device is actually, this comes in a 3x3 millimeter QFN. And all of these devices are in 4x4 millimeter QFN. So not a big difference, but this is the smallest out there. Having said that, so this was our quick introduction about the TI's new pin-to-pin stepper family that's all released, except for this device, the 8425, which is coming in early 2021, and all available on TI.com. Thank you all for your time. And now we would like to open up the floor for questions, and we would take the questions that you have on chat. But feel free to ask any questions. Dipankar is here. He was the one who basically designed this device as well.
Thank you, Renita, and thank you everybody for attending today. As a reminder, you can go on to www.ti.com/NPU at the end of the day today to get the recording of this and the PDF version of the slides. And we hope to see you next week on January 28th for the topic eFuses and switches. So we will stay on for a little while, and if you have questions, please ask them in the chat and we will help you answer them.